I would like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
Hello and welcome to the Materialism Podcast, an exploration of the past, present, and future of material science. As always, I'm your host, Taylor Sparks, and I'm joined by my co-host, Andrew Falkowski. Andrew, how you doing?
Doing really well. Excited for this episode.
Absolutely. Now, we were supposed to record this on Sunday, but I had just finished a 100-mile race, and I was not in a good way. So thank you for delaying a couple days to record this. We are joined by Patricia Kooyman. Am I saying your name right?
Correct.
She's from the University of Cape Town in South Africa. You've come a long ways to be here in Salt Lake City. We're so excited you're here.
Yes, thank you. I'm very excited to be here. Congratulations on finishing that
my gosh.
course, by the
well,
way.
I don't know if I really finished. That toenail, at least one part of my body did not finish the race with me. He's gone.
It'll grow back.
It'll be back later.
Yeah. I'm actually in town because one of the best microscopy conferences in the world is held annually in the United States. It's the Microscopy and Microanalysis Conference. And this year we're in Salt Lake City. So it rotates every year to a different city. So this year we're in Salt Lake City. So that's what brought me here.
We're so excited about you here. In fact, I've gotten all these emails from people from out of town saying, hey, Taylor, I'm in town. Let's get together. I'm like, oh, right, the conference. So we are delighted. Now, Patricia, you are an expert in transmission electron microscopy. And listeners of our podcast will go back and remember that we had a previous episode on electron microscopy where we touched on the notion of TEM, but we haven't gone into detail. Today, we're going to go into a little more detail, and specifically, we're going to talk about something called Operando TEM. What in the world is that, Patricia?
Well, just to recap very briefly, transmission electron microscopy is a microscopy technique where you use, instead of light, you use electrons. And because of the small wavelength of electrons and the high energy, you can get much more detail than with light microscopy. So in principle, with transmission electron microscopy, we can see atoms. That's the resolution. We can really go down to 1 angstrom or even smaller with the newest techniques. So we can literally see atoms. The problem with ordinary transmission electron microscopy is that it needs to be in a high vacuum, because any gas molecules that are present in the microscope column will interact with your electrons and will result in random noise because the gas molecules are moving around. So they will introduce a lot of random noise, just like a background haze. So that's why normally you need to be in high vacuum.
And the effect, it kind of is like a blurry image, almost out of focus, because you're getting a lot of scattering of these electrons.
Correct, yes. You introduce a lot of random noise, so your image, it's like the image is enveloped in fog, in mist, instead of just your clear image, if you have a lot of gas molecules present. Which means that you can only study sort of frozen, room temperature frozen samples that are not moving. And that's very interesting for many material science problems, but for some problems, you want to study samples as they are interacting with gases or liquids. So I'm at the University of Cape Town now. I've been here for 10 years. But when I was still at the University of Delft in the Netherlands, we had a team of 3 people. The Professor Henny Zandbergen, he's emeritus professor now, and clean room microelectromechanical systems person Frederick Kramer, who unfortunately left the field. And myself, we were the core team in trying to develop a system where we could actually study heterogeneous catalysts, which is my other specialty, while they are doing their catalytic reaction.
So I'm trying to put myself in your headspace when you were a PhD student. You have catalysis where you want to react with gases, and yet you have this instrument where you can't have gases. What was your strategy? Like, what were you thinking about how to test this? What was your first idea when you were exploring this?
Well, I was a postdoc at the time. There were already some people fiddling around with somehow making windowed cells where you would retain the gases in a limited volume. The other approach was to put a very low pressure of gas in most of the column. But that meant that you can only go to about 5 millibars.
Yeah,
So
the image starts getting ruined, right?
exactly.
And you can actually damage the source. I saw in one of the papers you wrote, right?
Correct.
What exactly happens there? I don't quite follow that.
Well, the electrons have to go through the whole column and through the sample.
yeah.
So you can't like shut it off with a window because electrons, if you put any
Yeah, they have to be
material-
able to travel through it.
Exactly. So the electron source is, there's different materials that we can use, but the principle is that it's a very, if possible, an atomic tip
Uh-huh.
that is put under very high current. And then there's a voltage difference between the tip and what we call the Wayne belt filter, which pulls out electrons from that tip, which is at high temperature and high current.
And if gas is there, what happens?
If any gas, even normally inert gases like nitrogen, if they hit that hot tip, it will immediately react with the tip and it will destroy the tip. So then
I
you
see.
lose your electron current.
Okay.
Yeah.
So adding gas to the column of the TM is not a great option, is what I'm hearing from you.
Correct.
But there had been some attempts to enclose a very small, like a capsule,
Yeah.
where you're having the reaction
yeah.
take place within that.
People had been working on that, but then it was just a batch. So they couldn't flow the gas. You could put in gas
Oh,
and
I
close
see.
it, put it in the
Like a
microscope.
sealed ampule or something.
Exactly.
Okay.
Yes. Yeah. But we were like, well, if you use a catalyst or whatever material in practice, you're not putting it in a closed ampule. You're flowing your gases over your catalyst. So we wanted to do that in the microscope. So then, in the end, we developed what we call the nanoreactor, which is a closed cell where you actually have to adapt your whole sample holder because you have to have gas lines going through the sample holder and you have to have electrodes going through the sample holder because you also want to heat
Sure.
your catalyst because most catalysts don't work at room temperature. You
Or
have to go
perform electrochemistry, right?
That's a different setup, but that's now also possible. Yeah.
I see.
Yes.
So how big are we talking? Is this whole capsule, is this like the size of a...
It's 3 millimeters wide
Okay.
and 5 millimeters long.
Pretty small.
Yes, it's
Okay.
pretty small. It has to fit inside the transmission electron microscope.
How big is the beam of a TEM?
That also depends a little bit, but it's in, you can...
A couple millimeters though?
No, nanometers.
Oh, it's tiny.
Yes.
Oh, of course it is. Yeah.
And
Yes.
what does sample preparation look like at that scale? Is that
Yeah, you need very thin samples because when you go, again, depending on the material, but it has to be in the order of 10 to 100 nanometers thick, the sample. So for catalysis, actually, it's fairly easy because most heterogeneous catalysts are powders. So you can just crush the powder and put that in your nanoreactor. And then you will have some areas that are thin enough for imaging. Alternatively, if you know a little bit about catalysis, we often make supported catalysts where we make nanoparticles that we then support on aluminium oxide, silicon oxide. What you can also do is just make the particles and support them on the window material, which we started out with silicon nitride. We also experimented with silicon carbide, but that has developed since then. So there are quite a few
So
different materials available.
Why those materials? Is it the electron attenuation, I'm guessing?
You need materials that can be thin, amorphous, strong enough, electrically conducting, because if it's not electrically conducting, all the electrons get trapped and then you get all kinds of weird charging.
Yeah.
It's almost like static electricity.
Oh, totally.
where
Yeah,
it
it would ruin
builds-
your image.
Yeah, exactly. So
Silicon nitride, is that conducting? I didn't think it was.
if it's a thin layer, it's
Interesting.
because it's a silicon chip. So the silicon itself is conducting, and then you've got a thin layer of silicon nitride.
Okay.
Yeah.
So the entire thing, the entire apparatus, the electrons still have to travel through this. So it is extremely thin.
Yes.
200 nanometers or so, did you say?
the thickness of the gas layer is up to about 5 micrometers.
All right, because that's just the gas layer. And then the solid, the window material, if you will.
The windows are
very thin.
Very thin. The commercial ones that you can buy now, so at the moment there are 3 main companies that sell similar systems. Alphabetically, it's Dense Solutions and Hummingbird and Protochips. So the commercial windows are about 50 nanometers thick,
Okay.
but the ones we made were more like 15. But they are a little bit less robust. So of course, the thicker you make them, the more robust they are. But the more background noise from the windows you get. So
it was interesting reading the article you sent us ahead of time that in the early days they had single crystals of graphite, and they're doing the whole Scotch tape trick where you exfoliate it away to a certain thinness. And that sounds like, okay, great, you can get it thin like that. But then there's all this extra work because you have to like release it onto water. You have to get it onto some sort of substrate, sapphire, bake it, get it back onto water, then get it onto your cell. This sounds complicated.
It is very complicated. Nowadays, because the techniques have developed so much, those companies make those chips or the nanoreactors in batches, just in clean room facilities, just like you make computer chips. And there are also more and more companies now. I've seen at least 5 or 6 now at the conference that offer custom built chips or nanoreactors.
Is this for different reactivities with gas, I'm guessing, or
different electrical things, different combinations of electrodes, gases, different materials? Yes.
So how cool, you were there from the beginning. Tell us about the process. Like, what was this like to actually build up this nanoreactor, which has now been commercialized by multiple companies?
Yeah. Well, it was awesome. I learned a lot about clean room technology, which I didn't know. But that's why we had this team of people with the one clean room specialist.
Roughly what years are these happening?
I think we published the proof of principle in 2014.
Okay.
Yeah. So it's not that long ago.
No, really, that's pretty. In fact, I was pointing this out before we started the episode. It's remarkable. This whole concept of seeing atoms is incredible to me. Like in my lifetime, this became a thing that happened. And now not just seeing atoms, but seeing them at crazy resolution and now seeing them do stuff because we can do reactions, Operando reactions.
Yes.
Pretty amazing.
Yes.
Just in the last 10 years or so that we're starting to see this happen.
Yes, definitely. So yeah, we had this concept of we want these electron transparent windows. So then we had to search for materials that would be suitable. And then that's why we started collaborating with the clean room people who were used to making computer chips, which also starts from a silicon die. So they had all the techniques. And then it took us like 8 years before we had a working prototype. And then of course you have all these, each time you try an experiment, you run into a different problem that you had to solve. And one interesting problem is that organic material decomposes easily in the electron beam.
Oh, the electron beam itself.
Yes.
Is it heating or what?
It's usually like 200 kilovolt electrons, so that's a lot of energy. So organic material decomposes very easily. So like I said, you have to put gas pipes and electrodes through the sample holder. The sample holder itself is like 20 centimeters long. So the technician who was helping us, the fine mechanical workshop person who was helping us build the reactors and the holders that we were designing, to keep those very thin gas lines in place, he had used beeswax.
Oh, really?
And then when we started doing our experiments, all we saw was this buildup of
paraffin everywhere.
Exactly. Well, it was,
I guess, decomposing into smaller.
And then it builds up into just solid carbon, and it ruins your image again. And then it took us like 5 weeks to realize that he had used beeswax. So then we told him to use a silicon rubber, and then that problem was solved, and we could go on to the next problem.
It's one of the challenges of working with a large team is somebody does something, and unless it's communicated, it takes a little while for everyone else to figure it out.
Exactly.
Now, are these chips consumable, or can you reuse them?
No, they're consumables. You can't reuse them. For some processes, you do use them for like 2 or 3 days in a row because you're doing a whole range of experiments and temperatures and gas compositions. But it's very difficult to really get the the catalyst or whatever you're loading out of them and reuse them. So but at the moment, if you buy them commercially, the standard ones, I think they're about $10 each. So it's not that bad. Yeah.
Wow. That's amazing.
Yes.
You mentioned that these are being made out of lots of different materials. Is that due to the reactivity of different materials with the gas, or with the electron beam itself, or with the catalyst?
Mainly with the gases.
Okay.
Yeah.
And what sort of materials are being used?
I think people are looking into, actually we're going back to graphene, because it is super electron transparent.
Sure.
And also the techniques to make it
we've gotten a lot better.
Exactly, have developed tremendously. But also materials that people can sputter, and people are trying to make chips that have a very thin layer of silicon oxide, because silicon oxide is one of the commercial supports for catalysts. People are trying to make aluminium oxide, all kinds of different materials. Sometimes the main chip is completely silicon carbide with a thin membrane of something over the windows. So there are just about anything you can think of. People are trying or are going to try in the near future.
Okay, so this is fascinating. We have the ability to observe reactions as they happen. We're hoping that the electron beam itself isn't part of the reaction. We want it to be just a silent bystander to tell us what's going on. But
yes,
now we have the ability to observe these. Why does this matter to material science?
Well, on the one hand, the electron beam is often not only a spectator because of its high energy and because of it's got electrons. So it will interact with your materials a little bit. So if you're really doing proper science, what you do is you study your reaction while it is running, and then you go to a different area that hasn't seen the electron beam to see if your material has developed in the same way as the material that was exposed to the electron beam.
Is it pretty common that they're different?
Sometimes it's different, sometimes it's the same. But yes, it definitely happens quite often that it's different. And then you always use a combination of techniques. You never only rely on the Operando TEM. So you will also do ex situ before and after studies, and you will do the before and after studies in your nanoreactor. So studying parts of the material of the catalyst that haven't been exposed. But the thing is that now we can actually see what happens during the catalytic reaction. So there have definitely been multiple cases where we now realize that actually what we thought was happening based on before and after is not what's happening.
That's so cool. Any cool examples you can point to?
So one big area of catalysis is Fischer-Tropsch catalysis, which is Fischer-Tropsch catalysis is where you make synthetic fuels like biodiesel, sustainable aviation fuels. You can make it from a host of starting materials, because all the organic starting materials, it can be crude oil, it can be natural gas, it can be biomass, it can be coal. You can convert those into what we call synthesis gas, which is a mixture of hydrogen and carbon monoxide. And when you've got that mixture, doesn't matter what the source was, you can do the Fischer-Tropsch process, which knits them together into long-chain hydrocarbons, which we can use for transportation and also for lubricants. One of the catalysts that is used is an iron-based catalyst. So you put iron oxide into the microscope, or into the reactor, also in the chemical plant in large volumes. You start with iron oxide, but we know it's converted into iron carbide. What people thought based on these before and after and intermediate steps was that the iron oxide, we usually start with Fe3O4.
Okay.
Then you reduce it to Fe2O3. And then it's reduced to iron carbide. So what people thought was that the small particles of Fe3O4 were reduced to small particles of Fe2O3, and then those were broken up into small particles of iron carbide. But what we've seen is that you actually grow huge particles of Fe3O4 before you go back to small particles of iron carbide. It's very
And
fascinating.
the catalysis plays a role in the growth of the Fe3O4 first?
No, it's just a carburization. So you use some of your carbon monoxide to create your iron carbide.
I see.
But that process of making the iron carbide is completely different from
How cool.
what people thought before.
And you can see it, so
we
you
could
know it's
see
happening.
it happening. We've published it. You could just see it happening.
That's amazing.
Yes.
And how cool is it that we can live in a world where publishing allows us to put more than just static images either? I believe a lot of these
Yes.
now include videos, or at least
Yes.
there's supplementary material.
Supplementary
that people can
information,
watch.
videos, definitely. Yes.
Another thing I saw when I was looking through the article that you sent was oftentimes when catalysis was described to me, it's often that this molecule and this surface are going to interact, and that this will leave, or some reaction will take place on that surface. But it seems that oftentimes these are accompanied by somewhat large atomic rearrangements by the catalysts themselves and the molecules, and it sounds like this has opened up the ability to see that now.
Correct. That's also one thing that we showed in really at the very beginning, where it was known that carbon monoxide oxidation on platinum nanoparticles can give oscillations. So it was known on the lab scale, and Ertl got the Nobel Prize for showing it in a scanning tunneling microscope. But that's still, the scanning tunneling microscope uses a flat surface, so it was still a model catalyst, not a real catalyst. So what we did is we prepared the platinum nanoparticles using the windows of the nanoreactor as the support material. So we really did the procedure that you would normally do to make a platinum nanoparticle catalyst on aluminum oxide. We did the same procedure without the aluminum oxide, but using the windows of the nanoreactor as the catalyst support material. So you start with the platinum salt, which you dissolve in water or ethanol. Then you load that into the nanoreactor. You dry out the solvent, in our case ethanol. Then you heat it in air, and then you reduce it. So we did the reduction in the microscope to make the metal platinum particles. And then we started admitting carbon monoxide and inert, just to make sure that we have a slow reaction so that we could see what was happening. And a little bit oxygen, we had, I think we had 10 times the amount of oxygen that was required to oxidize all the carbon monoxide. And then we started this experiment, and we saw these oscillations happening. What we first saw, because there's a feedback mechanism for the temperature, so we would set a set temperature, and then we could see how much power input the system needs to keep the temperature stable. So suddenly the temperature started fluctuating, or the power input started fluctuating to keep the temperature steady. And then our first thought was that the nanoreactor was broken. So we took it out, took a new nanoreactor, went through the whole process again.
And you see it again.
And we saw it again. And then we were actually doing those experiments at Helder Topsoe company in Denmark, who was one of the partners towards the end. They joined the consortium when we already had a prototype. But they had a really good microscope with some extra safety features just in case the nanoreactor would be leaking. Well, fortunately, they're hardly ever leaking, so that wasn't an issue. But their facility is very close to a small railway line, which runs every 20 minutes.
Oh my gosh.
So when we saw these fluctuations, everybody was looking at their watch like, but there's no train coming by now. So then we were sort of starting to think, okay, maybe this is real. So after a while, these oscillations stopped. And during these temperature oscillations, we also saw that the larger nanoparticles were clearly changing morphology big time. And what we also saw, because we had a mass spectrometer, or sometimes they call it a residual gas analyzer, depending on which company you're talking to. What we also saw was that when there was no oscillation we had about 50% of the carbon monoxide that was being converted. But then when it went into this oscillating mode, suddenly we had all the carbon monoxide being converted. So that was really related to the oscillations. And then somehow, we still don't know exactly what triggers it or what stops it. Sometimes after 10 minutes, sometimes after 20 minutes, it would stop oscillating and it would drop back to this about 50% conversion.
Is this a fouling or something that happens, or?
We're not sure, because sometimes after half an hour or 40 minutes, it would spontaneously start oscillating again. We could always trigger the oscillations by increasing the temperature with 0.5 degree. So we're still not sure what triggers those oscillations.
But how cool that you have the capability to make these measurements in real time. I'm curious, is time and your the time resolution, right, the time step that you can actually measure, is that limiting your ability to measure stuff that you care about? Or is it really, really fast in TEM? I don't know.
It was okay-ish back then. Now with the new camera developments,
amazing, I'm sure.
There's cameras that can do like 1,000 frames per second.
Oh.
Yes. Back then it wasn't that fast. I think we had about 100 frames per second, which was enough to see the changes in our particles. Yeah. And then to really confirm, we took that second nanoreactor to Delft, where we had a second copy of the holder and the gas system. And then we could reproduce those oscillations at Delft. And then, only then were we confident to publish
now we can publish.
it. Yes, exactly.
I'm glad that you're skeptical of your own stuff. I try and teach my students this, like, I don't want to see your best model. I want you to be skeptical of it and then come show me the data.
Exactly.
Well, very cool.
Yes.
Other cool examples of things that we've learned as a field of material science using this technique?
There are so many
I'm sure.
interesting
I remember the
things
first time I
going
saw
on.
lithiation happening in a battery. I thought
Yes.
that was so cool.
Yes.
You could see the cathode get lithiated from the outside in. I remember I saw the first like cracks and the dendrites growing. All this was possible by cells that you can see them in Operando, I suppose.
Yes. Yeah. One of the things that you see more and more now is people working on bimetallic or trimetallic nanoparticles and seeing how you can start with a core shell particle and then heat it and see how it either becomes mixed or it becomes a separated, what we call a Janus particle.
Yep.
There are all kinds of different experiments that people are doing. There's so much going on at the moment. It's really fascinating.
It sounds like in a lot of these cases, it's some sort of macroscopically observed phenomenon, and then shrinking that down and setting the experiment up in the right way that you can then observe the mechanism at the atomic scale.
Yes.
Has there been any research in the interplay between this and maybe some simulation codes for materials?
Yeah, there's a lot of that going on, but I'm not a big expert in simulation. So if I want to do anything like that, I collaborate with people who are experts in simulation.
I'm curious, what are the sort of challenges, like you're here at a conference, right? And I love going to conferences because you hear this sort of stuff like, here's the bleeding edge of what we know we can do. So in this field of Operando TEM, what's the bleeding edge? Like, what is it that we can't do? What are the challenges that we need to address going forward?
Well, there's still a lot of unknowns about the effect of the electron beam.
For sure.
In the gas phase, it's a little bit easier. There are also people who are developing, and they're also already available commercially, liquid phase, similar nanoreactors.
Does your resolution just get tanked with all the liquid? Because you got so many more atoms that it's hitting.
Yes, but you can go through to fairly thin layers of liquid. The problem is in the liquid, you get so many more radiation effects.
What do you mean?
Because
like when they get hit by the electron,
yes.
they then irradiate?
Yes.
I see.
So you can get dissociation of, especially water is very sensitive to the electron beam. So, but many useful processes run in water. So you can't go to like an ionic liquid or whatever and reproduce the process that you actually want to study.
And you can't reduce the energy of the TEM without losing resolution and penetration as well.
Penetration, yeah, especially. Yeah, so
tricky.
So it's always finding the balance between the energy of the microscope, but if you go to lower energy, then sometimes there's additional effects that occur. It depends very much on which materials you're studying. So the radiation effects, the effect of the electron beam on your process is still something that has many unknowns, that people are studying them. And then once you know what's happening, then the next step is how can we prevent it?
Yeah. One question I had when I was thinking about this, of what might potentially be a challenge is, anytime I see these microscopy techniques and things like that, where you can generate massive amounts of data, now we're doing video. Well, what are you doing with all that data, right? It used to be you could collect your data at the end of the day, throw it on a thumb drive, but now you're talking about, I'm guessing, terabytes or massive amounts of data.
Yes.
Which suggests to me probably the need for edge computing, where the place where the data is being generated on the microscope, you're doing some sort of pre-processing of the data to get out what you care about, and you're taking that away as opposed to terabytes of images.
There are more and more software packages that can deal with these things, because additionally, you've got data from different computers, because you've got your imaging, you've got your temperature, you've got your gas composition, etc., etc., etc.
All these have to talk to each other. They're all probably proprietary.
And the thing is, you want all those data synchronized.
Right.
Because that's important. With those fast changes in your materials, you need those data synchronized. So when we were working, one of our PhD students wrote an open access software program to synchronize all those computers. But then indeed we had to get permission from all the different manufacturers.
And are they pretty good to work with? Like, are these companies good to work with in that way?
Some of them are good to work with. Some of them are a bit more difficult and say, oh, if you do that, then you lose warranty or whatever. But nowadays, the companies that sell these complete systems, their software is also improving very quickly.
Glad to hear it.
So they have the deals with the microscope manufacturers that if you use their software, it's okay to hook it up to the microscope and they can synchronize everything. I mean, I saw a tutorial just at lunchtime, and I think they said there were 80 parameters in the metadata that you could individually select whether you wanted to display them in your results or not. And it's all time synchronized. So these developments are very, very fast. And of course, there's a lot of AI, machine learning,
I'm sure,
neural networks that are being used to help analyze the data.
Yeah. So what does the future look like? What's coming down the line in this field?
What we're seeing at the moment is the combination of even multiple techniques within the microscope.
What do you mean?
So people are adding like a laser so that you can do photocatalysis or other photo processes. People are looking at doing the imaging and electron energy loss spectroscopy and EDX, energy dispersive elemental analysis simultaneously. People are looking at doing transmission electron microscopy and scanning electron microscopy simultaneously, putting an atomic force microscope inside the transmission electron microscope.
It sounds expensive. These tools are already multi-millions and now you're putting them together.
Yes, but I mean, it's so exciting if you can get all these data simultaneously from the same material.
Absolutely.
Because what we've been doing and what we are still doing is like, okay, we have this sample and we study it in the TEM, and then we study different particles from the same batch in the AFM.
Sure, and you hope they haven't changed. You hope
that
they're, but now
and you hope they're doing exactly the same thing. So if you can, can record all those data really on the same particle, that's gonna make a huge difference.
Maybe one final question is there something you're interested in studying but currently can't due to the present technological limitations of this?
There's quite a few processes. Like when you do the Fischer-Tropsch process, you start building up these hydrocarbons. So that's something that's still an issue, that your image gets clogged after not too long. And then there's another field of catalysts that I work on a lot, which is microporous materials like zeolites, metal organic frameworks. They're quite beam sensitive. So they get destroyed. If you have a platinum particle, it's stable in the electron beam. You can beam it with an electron beam and it stays a platinum particle. But if you put a zeolite, which is very porous silicon aluminium oxide, which contains crystal water, and it contains positive counter ions.
Yeah.
So
Electron beam. wreaks
electron
havoc.
beam, vacuum. Well, in the Operando we don't have vacuum, so that problem is
Yeah.
eliminated. But still, so
Do
these
you
get
see like changes in the phase, or what do you see?
it amorphizes.
Oh, okay.
Yes. So then you've got a bunch of
Then you
amorphous
lose your
material.
channels.
Exactly.
Yeah,
exactly.
you've lost what it's supposed to do.
Exactly.
Interesting.
So there are still lots of challenges.
So room for scientists to do amazing things going forward.
Definitely.
Patricia, it's been awesome to have you here. Thank you for traveling
having
all the
me.
way to Salt Lake City. It's been fun to have somebody in person in our studio. And I've learned a lot about Operando TEM this episode. Appreciate it.
Well, it was a pleasure to be here. Thank you for having me.
Absolutely. Hey, everybody, this is Taylor. Quick announcement. We have an awesome new sponsor for our show. It's Momentum Transfer, and you're going to be hearing more about them because they are rad. But for right now, I want you to grab a pencil and write down September 29th to October 1st, 2025. In Bari, Italy, which is beautiful, by the way, right on the coast, there is a workshop on X-ray diffraction, powder diffraction techniques that Momentum Transfer is putting on, and you don't want to miss it. If I go back in time to me as a graduate student, I remember trying to figure out how much of different phases were present in some of my samples. And I knew it was possible, but I had nobody to teach me how to do it. I had to go to great lengths to figure out how to do Rietveld refinement. It was a pain in the butt. It was expensive. It was really hard. And nowadays, it is so easy to do. And this company, Momentum Transfer, is actually doing a very inexpensive workshop where you can learn about it. It is only 150 euros if you're a student or a PhD. It is only $250 if you're an academic, and it's only $550 coming from industry. So it is a steal to learn how to do it. You will learn all about the fundamentals of powder diffraction as well as their practical applications. You're going to learn how to do things like phase analysis. You're going to learn how to use databases like the PDF 5+, JadePro, or QualX2. On day 2, you're going to dive into structure solutions. This is where Rietveld refinement happens, right? They do it with Expo and the Topaz software. And then the last day, they're going to introduce more advanced topics like total scattering, pair distribution function, even how you get microstructural characterization like size and strain out of this process. So I cannot recommend this enough. If I could have gone back 20 years and told grad school Taylor about this, he would have been jumping on it. So I hope that you will take the opportunity to go see a beautiful part of Italy and learn from the pros. If you want to learn more, it is momentum-transfer.com/IWPD 2025. We want to throw out a special thank you to the sponsor for today's episode, the American Ceramic Society. And today, we want to point out a couple of resources they have available related to manufacturing with some online on-demand courses. So ACERS, or the American Ceramic Society, you heard us talk about them, their online learning center. You've heard us mention that you can get a sweet $100 off the next on-demand course registration if you use the code Materialism, all caps. Today, we want to mention a couple of the courses they have to offer. There's drying of ceramics, glaze manufacturing for industry, and statistical process control in ceramic processing, just to point out a few. Now, the first one I want to talk about is this drying of ceramics. If you remember our episode on Delta Faucet, we talked about the crazy problem that ceramic processing can have with yield. A huge amount of that has to do with the drying process itself. So I was delighted to see that they've got a full course on this. It goes in depth into the science behind this, how different processing insights can reduce your scrap rates, how you can adjust it, even accounting for seasonal changes with weather or humidity, temperature changes. It's going to be an awesome course. Highly recommend that.
Yeah, that sounds really valuable. The other one I'm seeing is statistical process control in ceramic processing. This is really important when it comes to ceramics because it's all about perfection when you're working with ceramics all the way through that process. And if you have deviations or things are out of control, it's going to affect your final product. And so taking a course that's specific to ceramics and some of the nuances and the probability distributions and models that are used in that sounds really useful. If you're interested in taking some of these courses, you can visit ceramics.org/materialism to learn more, or use the code Materialism, all caps, to get $100 off your next on-demand course registration. The Materialism podcast is also sponsored by Materials Today. You can visit materialstoday.com to stay up to date on the latest happenings in the material science field and read some of the fantastic articles that they've published. You can also head over to elsevier.com to find out more about their journals, books, conferences, and related programs.
And as always, we are so excited to have you guys a part of the show. I just got back from a conference where I met with so many listeners. It is absolutely unreal to be connecting with audience members from around the world. We would love, love, love to hear more feedback on what stuff you guys want to hear. You can find us at materialism.podcast@gmail.com or the @materialismpodcast on Instagram, or pretty much everywhere you want to find us. We are out there, and we love hearing feedback on the show. Special thanks to the people who make the music possible for this show, Alphabot and Kolobyte. We appreciate you. And that's it. We will see you guys next time.
The inventors of fire, electricity, magnetism, iron, lead, glass, silk, cotton, the makers of tools, the captors of lightning, the architect, the engineer, the musician, are all beneficiaries of the materials of this world and are bound only by their imaginations in manipulating those materials.